working on that. So in today's class, we will do an example of full state feedback, right? So if you recollect, we were looking at the problem of full state feedback where we wanted to essentially, consider designing the controller using the state space representation. And we wanted to, find the value of the control gain K such that, we got closed loop stability, right? So in other words, you and I want to place the eigenvalues of the closed loop state matrix at the desired location. Okay, so that's what we want to do. So in that regard, the question, the problem statement that we posed to ourselves in the previous class when we met 1 week ago was this, right? So we took a second order system and we wanted to figure out what will be the full state feedback controller that essentially provides, or that essentially ensures that, the closed loop eigenvalues are at -1 plus or minus j. Okay, so that is the problem statement. So let's get started. So the flow of the problem is the same, right? So the solution is the same, right? So what happens is that in any problem involving the state space representation, particularly with respect to control design, the first step is that we given the state space representation, you and I need to figure out the equilibrium state. Then we comment on the stability of the equilibrium state, right? How do we figure out the equilibrium state? We solve AX star to be equal to 0, right? So in this particular case, the state matrix A is 2, 3, 0, 1. So X star is X1 star, X2 star. It's a second order system. So if we solve this, we get a unique equilibrium state of the origin, all right? So that's what we have, right? So then, if we want to essentially comment on the stability of the equilibrium state, we need to solve for the eigenvalues of the state matrix. For that, we solve determinant of lambda I minus a equals 0. So if we calculate lambda minus a and take the determinant, in this case, it becomes very straightforward because we are having an off-diagonal term to be 0. So consequently, we get this as the determinant, and if we solve for the roots, we get the value of the eigenvalues to be 1 and 2. Okay, so we know that we have a unique equilibrium state. At the origin. Okay, so and that equilibrium state is unstable. Okay, so that's what we can find out. So you and I need to design a full state feedback controller. Okay, such that we can essentially so we need to ensure that the closed loop system is stable. So for that, what we do is that we go and form the controllability matrix. So as we know, for a single input, single output system, the controllability matrix is, if you go back, the controllability matrix was B, AB, A squared, B, all the way till A power n minus 1, right? So this is what we learned as the controllability matrix, right? So that's an n by n matrix for a single input, single output system. And when we have n to be 2, okay, when we have a second order system, this controllability matrix just comes out to be P and AB, right? Because n minus 1 is 1, right? So we can only go till A power 1, okay? So we only go till AB, okay? So that's what we have. So if we go back to our example, we see that we have the controllability matrix to be P and AB. We calculate AB. For that, we multiply the matrix A with the vector B. And if we look at this, we see that the two columns are not multiples of each other. And if we take the determinant comes to be -4. Okay, it is not 0. So the rank of the controllability matrix is 2. So consequently, the system is completely controlled. Okay, which is good. Now what we do is that, like, we go and calculate the closed loop state matrix ACL, which we know that is A plus B outer product K. If you do this, this is B, and this is the vector K, right? So we know how this works, right? So if we have the vector B written as B1, B2, and outer product K1, K2, the outer product becomes a 2 by 2 matrix, which will be B1, K1, B1, K2, B2, K1, B2, K1. Okay. So essentially, this is what you will have. And if we calculate the closed loop state matrix, you will get, this as the closed loop state matrix. Okay. So I think you will have this as the closed loop state matrix. And what is our design problem? We need to place the closed loop eigenvalues at -1 plus or minus j. So we essentially want to calculate the closed loop eigenvalues, right? Or the eigenvalues of the closed loop state matrix. So we essentially calculate determinant of lambda in ACL. So we take this ACL. Of course, right now we'll have in terms of K1 and K2, right? Because K1 and K2 are unknown. So if we process this, we get a second order polynomial in lambda, which is of this form. Okay, so we essentially have this as the closed loop characteristic polynomial. So if you remember, when we used transfer function representation, the denominator polynomial, right? 1 plus g of s of s, right? That was the closed loop characteristic polynomial. In this particular case, when we use the state space representation, determinant of lambda I minus ACL is the closed loop characteristic polynomial. So what we do is that we simplify it, and finally we get it in this form. Okay. Now we can observe that the closed loop characteristic polynomial is this. Let me write it and explain one key concept to all of us, right? So it is this. So now how do we typically can proceed? You and I can solve for lambda. This is a quadratic polynomial. So we can find the roots. Lambda equals minus b plus or minus square root of b squared minus 4ac by 2a, right? Using that, we can find lambda. But the complexity is that, like, that will be a function of k1 and k2, right? The algebra will become very complex, right? So what is an alternative? An easier way is that this is the closed loop characteristic polynomial, but the closed loop characteristic polynomial is also lambda minus lambda 1 decide times lambda minus lambda 2 decide. Why? Because lambda 1 decide, which is -1 plus j, and lambda 2 decide -1 minus j, are the desired eigenvalues, right? So they are the eigenvalues of the closed loop state matrix, right? That's where you and I want to place the closed loop eigenvalues, right? So the closed loop characteristic polynomial, the roots of the closed loop characteristic polynomial are the eigenvalues, right? So that's why we write it in this form: lambda minus lambda 1 decide and lambda product of lambda minus lambda 2 decide. If we substitute for lambda 1 decide and lambda 2 decide and calculate this, we get the desired closed loop characteristic polynomial as lambda squared plus 2 lambda plus 2. Okay, that is why I have written in two colors. Okay, the text in blue indicates the closed loop characteristic polynomial in terms of the controller parameters k1 and k2, whereas the text in green is the closed loop characteristic polynomial that we desire. So what should I do? I should just compare the coefficients, right? So what we do is that, like, we want the closed loop characteristic polynomial to be lambda squared plus 2 lambda plus 2. So we just compare the coefficients. The coefficient of lambda is -3 minus k1 minus k2. So that will be 2. And the constant term is 2 minus 2k1 plus 2k2, which is also okay. Now we just need to do the algebra, right? There are 2 equations, 2 unknowns. These are all linear equations. If you simplify the equation, you get the what to say, control gain vector to be minus 2.5 and minus 2.5. So this is a very what to say, unique case where we have both the controller parameters to be the same. This is not always true. Okay, so it can be any value. It is just that in this particular case, they happen to be the same. Okay, that's a different matter. All right, so we should keep that in mind. And some people will also call this problem as the pole placement problem, because poles eigenvalues are all like used interchangeably. So these are all jargons, right? So see, when we talk about poles, like you and I will immediately think of the transfer function representation. But when we, in fact, when we are doing this, we are essentially looking at, the state space representation, right? So which essentially deals with eigenvalues. Then the question that immediately comes is that how come we call it as the pole placement problem? It shouldn't be the eigenvalue placement problem, right? But these are all jargons, right? In the domain. Okay, so you and I need to respect it. Okay, so this is the overall process. So I hope this example has given us an overview of what steps we should do. So given the state space representation, what we need to do is that we need to first calculate the equilibrium state, then comment on the stability of the equilibrium state, right? Then we need to essentially look at controllability, and then we design the let's say controller, right? By looking at the by designing the closed loop eigenvalues. Okay, so that's what we have to do. Okay, so this is the entire process. Okay, so any questions on this process? So essentially, as your homework number 5, this is what I would suggest you to do. Okay, so please repeat the same problem. I think Arunachalam, we completed 4 homeworks, right? This is the 5th homework.
Yes, sir. Yes, sir.
So problem number A in 5th homework is this, right? For the same system, you just need to find out K1 and K2 such that the eigenvalues are placed at -2 plus or minus j. Please repeat all the steps. What do you think will change now?
So basically, this. So can you go up a little bit? Can you go up, sir? Lambda 1 and lambda 2, what you have written, sir? That will change.
Lambda 1 design and lambda 2 design will be changing.
Yes, sir.
Consequently, what will happen is that you will have the closed loop characteristic polynomial, right? Which we form, which will be lambda minus lambda 1 design times lambda minus lambda 2 design. Okay. See, till here it will be the same.
Yeah.
Till here, till this blue equation, it will be the same. Okay.
So coefficient of lambda and constant will change actually.
So now when you substitute for lambda 1, you get lambda plus 2 minus j. Then we get lambda plus 2 plus j. Okay. So this is what we have. Now, if we do this, what if we multiply it? What do we get? So I hope it's clear, right? So
lambda square minus 4 plus 4 lambda, and it will be minus. Sorry.
Minus 1.
So lambda squared plus 4 lambda plus 4 minus 1, right? So
yeah, right, sir.
Or minus of minus 1, right? Is it not? Minus j squared, right? So it will become plus 1.
Plus
right?
1 plus 1, yeah.
So you will get lambda squared plus 4 lambda plus 5. Correct? Is it not?
Yes, sir. Yes, sir.
Right?
That's
So
right.
if you expand, you will get this as the answer, right? So what happens is that like now instead of what to say this, okay, I think I have that. Okay. Anyway, you submitted as homework number 5 first problem. Doesn't matter. Although we have solved it now. So now what will happen if we compare the coefficient -3 minus k1 minus k2 will be
4, sir. 4.
4, and then 2 minus 2k1 plus 2k2 will be
5.
5. Please solve for k1 and k2. Okay, that is your homework. Okay. Right. So now you will get values of k1 and k2. Is it clear how you do it? Yes. Any questions?
It's clear, sir. If we get any question, we'll get back to you, sir.
Yeah. Okay. Fine. So I think that is the thing, right? So essentially, this is the first problem that I want you to solve. Okay. So as far as this homework number 5 is concerned, right? So essentially, we need to what to say do this problem. So then this is the sequence in which you solve control design, right? Okay. So and like we as a next step, like you and I are going to study the significance of the controller canonical form. So you remember we essentially did the controller canonical form, and like I told you that control design becomes easy when we choose a controller canonical form, right? Let's figure out how. Okay, so for that, let us consider a second order system which is governed by this, right? So now, how do you and I write the controller canonical form? If we go up, we discussed a few classes ago, right? So the controller canonical form for second order systems is this, right? So if we had a second order system, y double dot plus a1 y dot plus a2 y equals b1 u dot plus b2 u. This was the controller canonical form, right? The state matrix was 0, 1 minus a2 minus a1. The input vector is always 0, 1. Okay, and the output vector becomes b2 and okay. So please remember this, right? So we take this and then apply it to this particular problem. So when we go and do it, what's going to happen? I come down to our problem. So if we compare the coefficient a1 is 1, the coefficient a2 is -2, b2 is 1, and b1 is 0. Okay, so these are the 4 parameters that we get. Okay, when we compare it with standard. And then once we know these 4 parameters, we write down the equation, right? Because the state matrix first row is 0, 1. The second row is -a2 minus a1. Minus a2 becomes 2, minus a1 becomes -1. Okay, and the input vector is always 0, 1. Okay, and the output vector is b2 and b1. b2 is 1, b1 is 0. Okay, so I hope it is clear what this is. So we will come to this minimal realization next class. Okay, so we will learn about what is called observability in the next class. But right now we use the controller canonical. And we go through the same process, right? So we find the equilibrium state, AX star. When we do it, we get a unique equilibrium state at the origin. Okay, by now you and I are familiar how to do this. Then we essentially solve determinant of lambda I minus a equals 0. If we solve this, we essentially get the eigenvalues at -2 and 1. So if we look at these two eigenvalues, we can immediately observe that one eigenvalue is in the right of complex plane. So consequently, the equilibrium state is unstable. So we need to essentially stabilize this unstable system, right, using full state theory. So we essentially want to find the controllability matrix. So here once again, since it's a second order system, the controllability matrix is B and AB. So if we calculate this, this is what we have. and immediately we can see that the rank of the controllable matrix is 2. Okay, so the system is completely controllable. Okay, so that's something we can immediately figure. So we want to figure out the control gain vector K such that the closed loop eigenvalues are at -1 plus or minus J. What do? We find the closed loop state matrix. The closed loop state matrix is A plus B outer product K. We do the same steps, right? A is this. B outer product K. Now, if you look at it, the first row of this matrix will become 0. Why? Because the first element in the B vector is 0. The second element in the B vector is 1. So, in the second row, we just have K1 and K2. So, we will see that the closed loop state matrix takes a very simple form. Okay, K1 and K2 appear only in the second row with the controller canonical. Now, what do? We go and calculate determinant of lambda I minus ACL. If we do this is the closed loop characteristic polynomial in bold. And this is the desired closed loop characteristic polynomial in green. You and I have already figured out how to calculate that, right? That is lambda minus lambda 1 desired times lambda minus lambda 2 desired. It so turns out that you get it as lambda squared plus 2 lambda plus 2 once again. Okay, it's the same thing. Now, if you compare the coefficient of lambda and constant, we get one equation to be this, another equation to be this. Now, can you please tell me what is the advantage that you and I have here? Of course, I have written the answer, but I want you to explain to me. Hello? Hello?
So basically, K1 and K2 can be directly calculated now, because 1 minus K2 will be equal to 3. So we did not to solve linear equation of K1 and K2.
So in the previous case, when we did not have the controller canonical form, you see that either in this problem or here, right? What happened? We had a simultaneous system of equations, right? Is it not? That's what we call as a system of equations, right? Is it correct? So we need to do some more algebra to get the values of K1 and K2. But now with the controller canonical form, you see the simplification that happens. Each equation will have exactly one controller parameter. That is, there are two equations. In this equation, we had only K2. In this equation, we have only K1. So the calculation of K1 and K2 has become decoupled, and it's extremely easy to calculate, right? So we get K2 to be -1, K1 to be -4. Okay, so the control gain vector comes to be -4 and -1. Okay, so this is the advantage of the controller canonical form. Okay, so you put the state space representation in the controller canonical form and try to solve for the control gain K. Even if you have an nth order system, right? Let's say K1, K2, all the way till Kn, right? We have n equations. Okay, when we because the closed loop characteristic polynomial will be an nth order polynomial. Okay, here n is 2. Generally, it will be an nth order polynomial. So what will happen is that we will have n equations, n unknowns. If we did not have the controller canonical form, or if we did not use the controller canonical form, what will happen? It will so happen that we need to solve n simultaneous equations. Imagine the amount of computational effort that is required. Suppose, let's say n is 100. We need to solve for K1 to K100, right? 100 simultaneous equations. But if we have the control equations 1, 2, all the way to n, each will have exactly one parameter. Okay, so calculation of K1 through Kn will become extremely easy, right? We don't need to do any computation at all, right? You just can observe and then write K1 and K2. I hope the advantage of the controller canonical form is clear, right? Any questions on this? Any questions? I hope the advantage is clear, right? So if you use the control canonical form, when you do the control design, right? like things become very simple. So in other words, that's what I want you to do for homework number 5, problem B. Okay. So I have given you this particular system, right? You write it in the controller canonical form and then use full state feedback to essentially calculate the eigenvalues, calculate K1 and K2 such that the closed loop eigenvalues are at -1 plus or minus. I hope the second problem is clear, right? For homework. Okay. Any questions?
No, sir, it's fine, sir. Thank you.
Okay. So, so this is the concept of full state feedback and the advantage of the controller canonical form. And the full state feedback is a very commonly used, control method of the state space representation. There are various schemes by which you can get this control gain K. By that you have various methods, right? Now, the biggest challenge here is that if I'm a practitioner, let's say I'm an automotive engineer, right? And I use full state feedback for some application, right? I want to implement it. Now, if I have to implement it on a real vehicle or a real system, the question is, I require knowledge of the state variables X. Okay, who gives me that information? Because we know that U of t, the control input, is K dot xt. K, you and I will find, okay, through this design process. But then the question is, who gives us X? So even in the mass spring damper system, right? Let's say X is displacement and velocity. So we need measurements of displacement and velocity to even implement this full state feedback controller. Imagine, like the order of the system keeping on increasing. So even when you do the heading angle project, you will see that you will need lateral displacement, you will need yaw angle and so on, right? So the question becomes, who will give us all that data, right? So, and how do we know the state variables, right? To implement the, a controller, okay? So we need knowledge of X to implement the control, right? So the question is, if I want knowledge of X at each and every instant of time, I
Is
need
that sensor, sir?
a lot of sensors, right? Yeah, correct.
Exactly.
But that's not an engineering solution, is it not, Roshan? Right? Because how many sensors can you and I put? Like the product will not sell.
Of
Correct?
course, sir. Of
Right?
course, sir.
So then the question is, can we estimate X from limited measurements? So this is an engineering question, right? So you and I want to limit the number of sensors that we want to put, but using the sensors available, can we estimate? Essentially, we are not accurately calculating, but at least can we estimate such that the estimation errors are low? Okay, and that is what we will look at in the next class, where we will look at the problem of what is called observability. Okay, so the problem of observability, we are asking ourselves, can I estimate the state vector from limited measurements? We will see what it is. And one of the most common estimators which is used is what is called as a well-known Kalman filter. I'm sure even in your applications, literature and all, you would have heard about the Kalman filter, right? Okay. So essentially, the Kalman filter, is a state estimator, which is used for stochastic processes, and you can essentially estimate state variables using that Kalman filter. Okay, so we'll in the next class we will look at the problem of observability and also figure out how one can determine observability of system. Okay, and then use it for state estimation. And by the next class we will complete the theory. Okay, so we will meet on 1 minute. Today is what, 9th, right? So we meet on 15th and then like we will complete our theory discussion in that class. And then like you need to complete your project too. And then like we will meet on May 9th for our final exam. Okay, so that's going to be the plan, right? So any questions on what we learned today?
It's clear, sir.
So, but please do this homework number 5. Homework number 5 has 2 problems. Very straightforward. You know, we have almost solved both the problems to a great extent. But I want you to practice, right? And it's important from the perspective of the final exam also, right? So that is why when you ask me for practice problems, I told that we will do it, right? And then I will give you problems for homework also. Kindly practice. These are the kind of questions that you know you may expect in the final exam. Okay?
Sure, sir.
Of course, the final exam you need to practice all the questions, right? That we have been learning since midterm exam. Okay?
Sir, if required, after the next class, some doubts are there. Shall we have only one class after that, sir?
Sure, Arunachala, absolutely. So what we will do is we'll complete the lecture next class, next Tuesday.
Right, sir.
Then what we will do is that you tell me, okay? So last week of April or something like that, or first week of May, right? You tell me, and then like we can meet in the same spot, right? And then have a doubt clarification session, right?
Sure, sir. Thank you. Thank you, sir.
Thank you, sir.
Thank you.
Thank you very much, sir.
Yeah, and yeah, I think that will also help me in understanding how much of the information I have given also has been effective, right? I think I will also get feedback from the process.
Sure, sir. Definitely.
Okay, any questions on what we learned today?
It was okay, sir. Thank you.
Your batch is very silent, you know. So
The concepts are clear, sir, to be frank. That's why
concepts are
maybe.
clear, is it? Okay. So I hope it's had nothing to do with the hot weather and people are tired, right?
No, sir.
No, sir. No, sir.
Okay. So what about attendance? Arunachala, is everyone present? So
Everyone is present, sir.
then I marked everyone to be present. So then we will continue next Tuesday at 5 p.m.
Sir, one reason of silence could be that since your class is approaching towards end, so we all are like disappointed that we will not be able to meet you as frequently as we were.
We can always meet, no problem. You can always email me. You can drop by to IITM anytime. Okay. I think I enjoy interacting with your batch. So and then we can always continue to interact in the future also.
Thank you, sir.
Sir, one more help, sir. You had shared us the link for linear algebra. When we were going through that, we could find one more document on machine design, if possible.
What machine
video?
design?
Electrical machine design. 1 minute, sir.
I don't know what document I shared. Can you show me what that
Just
is?
1 minute, sir. 1 minute, sir. Yeah, I will take that document.
Linear algebra. What is it ED 5235?
Just 1 minute, sir. Just the system got running.
Okay.
Network, sure.
No, is it that power electronics for motor drive?
Yeah, power electronics, yes, sir.
Okay. That you could access that file also, is it? Okay.
Yeah.
Okay. I think maybe then that was an error from my end, because that is my notes. I attended the class as a student. I'm a mechanical engineer, right? But see, these last 3 years have been very tough, because I've been challenging. Because of course I have served on many administrative roles at IITM, but head of the department is a full-time job, right? Somehow I'm managing my teaching, my research, and this one. So despite that, I try to come on time to class because I have never been late to class, till now. right?
Yes, sir.
So, but with, being HOD, you never know, some emergency comes, like I need to attend to that, right? Why did I give that background? That ED 5235, I think that's what you are talking about, right? Power
Yeah,
electronics.
yeah, yeah.
So
Yeah.
that, if you look at the notes, that it will have the date as January 2022, right? At that time, I was placement advisor at IIT Madras. Okay, so I was taking care of institute placements, not at HOD. So till then, I used to attend classes every semester. That is, I wanted to go and learn new things, right? So I am a mechanical engineer. I don't know anything about electrical science, power electronics. So I attended the class. So I was a student, and that is my notes, right? I hope that clarifies, right? So,
Understood, sir. That was very, I mean, we could understand very easily from that notes. We were discussing.
yeah, please go ahead. Yeah, right.
That was very beautifully giving us the picture of, I mean, the electrical machines, DC motor controllers, things of that sort. We were discussing internally on that topic. Found to be intuitive, so we thought if you had taken that session and if you have the videos, then we thought of requesting for that video.
I think the clarification is that I attended the class, and these are the notes I wrote while the class was running. So. See, here I gave you the notes and then explained, right? So those are the notes I took when the teacher was teaching. Like my colleague was teaching. So yeah. So I was sitting in the class and writing.
Yes, sir. Yeah.
Yeah. So now, in fact, the irony is that I am not able to understand my own notes, because the best way to do the continue in learning is always to continue teaching, right? So that since I am a mechanical engineer, many of the electrical science courses, since I don't teach, right, I forget, right? So this is a classic example, right? So don't worry if you forget things, okay? Because only if you keep on using, the number, right? So I think maybe all of you should teach me power electronics from these notes, right? So since it was clear to you, now I am scrolling through it, I am not able to understand what I wrote. But okay, maybe then I shared the wrong folder. What is this linear algebra response?
No, that was.
Please neglect those things, okay? Because they are supposed to be information about research scholars who wanted to attend that optional class. Okay, maybe I shared the entire folder without realizing. Right?
Available, sir. Which was even interesting.
I'm sorry, what is it?
I mean, Prem was talking about linear algebra, so you've shared that link. In that link, we could even find this.
Yeah. And I think there is one more Google form with responses. Kindly neglect them. Okay?
Yeah, fine, sir. Yeah.
So that information, I asked my department research scholars who wants to attend, so that I can send them the link, right? Yeah. Okay.
Yeah.
So I think many of those research scholars have graduated now. So my own students and also other.
Sir, final exam will be like our maximum, sir. If same purpose.
Final exam, I think I would say a mix of things, sir, Roger. Okay? I have set one question paper. So what I will do is that I will wait for feedback from all of you. Okay. So depending on the questions that you ask me, I will see whether I want to modify it or keep it the same. Is that agreeable or not? No.
Yes, sir. Definitely, sir.
And once again, you can bring your one sheet page, right? One side. A4. Okay?
Yes, sir.
That you can.
Thanks.
Yeah. Anyway, final exam I could solve it in like within 7-8 minutes. So you get 90 minutes to solve. So no problem.
Right, sir.
Fine. Any other questions? All right. Good. Yeah. Any questions?